22nd. Okay, so we're going to get back to finding volumes. Before the break, we're doing the washer method. Huh? Good times. And so for this little do now here, you have to use the calculator. So if anyone needs to borrow a calculator, I have two right up here, if anyone wants to borrow one of those. But I want you to graph both of them so you can see the enclosed region. And we're going to revolve that region about the x-axis to create a solid of revolution. So you're going to go ahead, graph it, and decide whether you want to use disk or washer method. As far as the limits of integration go, you're going to have to use the calculator to do that. And see how far you can get with it. All right, and did anyone have trouble with that? It wasn't a take-home that I'm collecting, but you know, like I think it's going to be probably Tuesday of next week when I can test you on random questions from it. Did everyone find the answers? Yeah. Well, then forget it. We got to cancel it. We have got to cancel it. Ashley will not be here. But did you see where I had the answers? Either you go out and you buy yourself an Princeton Review, or you look on my e-board, and it's the first tab. Do you have trouble finding it? It might change like a 2 to a 3, like, but no, in no substantial way would I change it. Yeah, like really, really similar. Yeah, I should just tell you the answer, and then you could just check next to them. That would be better. Yeah. Okay, we'll do something like that. The reason I'm not going to give you the test this week on it is if you look at our little schedule for this week, you're going to have a test in area and volume on Friday. So we're going to finish that up today and tomorrow. We'll finish that up, and then we'll review. So that's where we're going. All right, so let me pause this. Okay, I want to go through this one with you because, you know, there's a lot in it. I know we're just coming back from the break. So the first thing, everybody should have graphed a region that I've outlined in green here. Is that what you saw? I know it looked like it was touching the y-axis, but you know those LN graphs, it just, the y-axis is a vertical asymptote, so that's why it looks like that. Now, the first thing you had to decide was if you revolve that area about the x-axis, are you going to get a disk or a washer? That's the first question you have to ask yourself, because solids of revolution are, you're either going to use disk or washer method. So you guys see it's a washer? When in doubt, you just look at the region. If it's not fully attached to the axis of rotation, then it's a washer. If it's fully attached, then it's a disk. So the slice is perpendicular to the axis would be a washer. So the first thing you do after you decide it's a washer, so the second thing you do, is write down the washer method. And you're going about the x-axis, so the thickness will be dx, a small change in x. And if you want to draw the whole thing, you don't have to. It's not important to Safi. I just like it. All right, so with the washer method, you have two radii you're going to have to discover. Now, the big thing is that you understand if you're going about the x-axis, the thickness is dx, because that means the only variable allowed here is x. Big R is the radius of the entire washer. It's the distance from the axis of rotation to the outside of your original region. And anytime you want to find the length of a vertical strip, which is what big R would be, you do y top minus y bottom. So for big R, y top is on this graph. And on this graph, y equals ln of x plus 2e. What's y bottom? 0. So for big R, it's the ln of x plus 2e. So I put that in this set of parentheses. Little r is the radius of the hole. It's the distance from the axis of rotation to the inside of your shaded region. So y bottom is still going to be 0, but it's y top is going to be y on the other graph now, on e to the x. So it's e to the x minus 0 for little r. So it's really important that you see for the washer method that big R, you go from the axis of rotation to the outer function, and little r, it's the axis of rotation to the inside function, which is which. Then the other thing you have to remember, or you have to do, I should say, is get the limits of integration. And since it's dx, we want to add up these washers from the smallest x to the greatest x. Now, I call them A and B here. On the AP exam, they tend to put this as one of the two calculator questions, not always, so I want you to be good at using a calculator for this kind of question. So just to go through this with you, let's take out the calculators, and we'll graph them. Just want to make sure you guys are okay storing the values as A and B. So you want to go to the y equals screen and graph them. I think most of you have those. I don't know the ideal window for this. I'll just leave it Zoom 6. So we're going to find that first point of intersection. We just want the x coordinate. Now I'm going to store it in A. So remember, to find points of intersection, remember how you do that with the graphs? Where was that? You have graphs, you want to know where they intersect. Second, calc. Okay, option 5. Now it's going to prompt you. First curve. Now if you're not in the domain of the LN, it's not going to work. You got to make sure there's some points down here. Make sure you're somewhere where I can, anywhere. But if I tried it here and I hit enter, it'd probably have a problem. So I'm just going to move over a little bit. Okay, now it's good. First curve, second curve. Yep, that's it. Here the x. And guess. Oh, close enough. So you should be getting an x value of 0.0119 something. Everyone getting that? So we want to store that in alpha A. Okay, I would jot it down. It's stored in alpha A. And the way you do that is you leave the screen. Remember how you leave the graphing screen? Second, the mode button right next to it. So second mode. And as long as the calculator expects you're going to store the x coordinate. So if you're storing the x coordinate of the point, you don't have to write x or anything. You just hit store. Store. Yes. When it said guess, you were probably closer to that second point. So if you want to go through it again, when it says guess, move over to you're closer to the first point of intersection. So, yeah. 0.011 something. I'll go over there. But for people that got it, you leave the screen, second mode, you just hit store, and then alpha A. Enter. You got to hit enter, it won't go into A. So the number we got was 0.0119 something. Right above the on button. If you wanted to store the y coordinate of a point, you'd have to hit alpha y store alpha A if you were interested in the y coordinates. But as long as you want the x coordinates, you just go right to store. It's expecting you to store the x coordinates. If you don't indicate them, something else. And then we got to do the same thing. I'm going to go and we're going to store the other, the x coordinate of the other point of intersection in B. So you got to go back to the graph, get that point of intersection, second, trace, option 5, first curve, enter, second curve. Oh, first curve, I think wasn't on there. So I had to move over. Okay. Second curve. And you should get a value of 1.795 roughly. 1.795. And I would jot that down and store that in alpha B. So do you remember how to store a value you just found on a graph? What do you got to do first before you can store it? Second, click, right? And then store alpha B, and you got to hit enter. It'll go in there. So the values that are stored in A and B should be here. Right? So those are our limits of integration. We're adding up these washers. I'm going to come over there in a minute, kids. I just want to set this other thing up. I'll go over. And then, once you have that, as long as you've written somewhere on your paper what A and B are, this is your work for your setup. Now, this will get you the volume. You got the pi, the big R squared minus little r squared. You got your dx, A and B. But I just want to make sure you know how to put this all in the calculator. Now you got all this. Because sometimes you actually have to get the answer. So we go back to our calculator. We don't want to forget about the pi. So pi, and then how do I get a definite integral in the calculator? Math 9. Now, I could type in ln of x plus 2e squared, but I want to be cool, don't you? You want to be cool? Who wants to be cool? Yeah, they want to be cool. Remember I stored ln of x plus 2e in y1? So we can, it's up to you, I can just type y1 squared. You know how to get y1 to show up? Vars, variables. We go over to y variables, hit function, and type y1. Now I can just say that squared. I mean, it's not saving you a lot of time, but can you imagine if it was like a really complicated function, not having to type it all in again? And then minus e to the x squared, or minus, I can do y2 squared. Oh, you know it, vars, y vars, function, 2 squared. Okay, so we put in, we've got the pi, the integral of r squared minus little r squared, then what? What do we need to put this in the calculator? Comma, x, comma, alpha a, comma, alpha b. Hopefully I didn't mess up any parentheses. And there you go. Good stuff. Right, let me pause it for a second while. Okay. So the thing is, when we were doing the washer method, oh, I got to give you the answers for the ones we didn't do. I was going to check it. I started checking it earlier today, and it was pretty lame, the homework attempt. So let me just go through these. With the washer method homework that you guys had, just the worksheet finishing the examples, this is number 2, if you want to check that. If you didn't get it, you don't have to write all this because we don't have time for you to copy all that down if you didn't do it. What you want to do is just check that you were using the, the washer method, that you filled in the big R and the little r correctly, and your limits of integration are good. The answer for 2 is pi over 6. Yes. No. It's going to be dy, so it'll all be y's. Yeah, but every time it's dy, to get r or the 2 radii, it's always going to be x right minus x left. Whenever it's dy, you're going to be doing x right minus x left. Whenever it's dx, you're going to use y top minus y bottom to get the r, or the big R and the little r. All right, let's take a look at 3. I don't know which ones we did in class. This was, you had a top, you had a part of a circle and a line. You're rotating this about the x-axis. So you want to see if you got the big R, the distance from the axis of rotation to the outer function was y on the circle graph. All right, that was the rad 25 minus x squared. And little r is 4. You want to check that your radii are good. Your limits of integration for this one should have been -3 to 3. I actually did see a lot of people that had this. The answer to this one's 36 pi. Make sure you have this set up right. Let me get that one right. I think it's less than 36 pi. Okay, so what would that mean? Did you do it on the calculator or by hand? If you did it by hand, I mean, maybe you plugged the numbers in the wrong way. Did you have this one first and then that one? Okay, so your big R and your little r are right. So switch the limits. I think maybe when you plugged them in, maybe you plugged in the -3 first. Because that should have. All right, that was 4. You had this triangle here, and you were revolving it about the y-axis. So again, the washer method, because you got a space in here. So big R is just 8. Little r it's going to be x on the line. You had to solve for x on the line. You know, sometimes they don't give you what x equals. You have to realize, oh, if y equals 8 minus x, it's up there somewhere, then x equals 8 minus y. You got to solve for x. And the limits of integration, since this was a dy problem, you're going from smallest y to greatest y, so 0 to 8. And they're saying, what is the answer? This one came out to be 1,024 over 3 pi. So if you want to check your work, it's 1,024 over 3 times pi. But that's the important setup up there. And the last one, this was the area enclosed by sine and cosine curves in the first quadrant. So big R, we're going about the x-axis, distance from the axis of rotation to the outside function. That was just y on this graph, which is cosine x. Little r, the distance from the axis of rotation to the inside of your shaded region, which is just a y on this graph, which is sine x. You could not have done this one by hand unless you knew the identity. You can't integrate cosine squared minus sine squared. That is an identity, does equal cosine of 2x. So you could then use u substitution. You could put in a 2 and a half on the outside. But this one you probably had to put in your calculator. But that's why identities are important. So you know, you go to integrate, you can't do it. But oh, the substitution, you know, it's kind of fun. So yeah, this one worked out to be pi over 2. Lovely. All right. Don't worry, kids. We're still doing disk and washer. But today, you know, like it always seems like y bottom 0 or x left is 0, right? Doesn't that get boring sometimes? Don't you wish it wasn't always just 0, minus 0, minus 0? Well, those days are over. Because today, we're going to take a region and we're going to revolve it about, not the x or y axis, but about some other vertical or horizontal line. And what that's going to do, it's going to change y bottom or x left from being just 0 to some other number. It's going to be interesting. So, first one, we got to always identify the enclosed region. So let's graph x squared plus y squared equals 1. What does that look like? Circle, right? With a radius of 1. Right? Then we've got the line, so this will just be what up here. We have the line y equals 1. What does that look like? What kind of a line? And what's a line? Horizontal. Excellent. Here's the line, y equals 1. And then x equals 1, vertical line. So first thing you always have to do is identify the enclosed region, the area that's enclosed by all those graphs. Hopefully, you see it's just this region in here. Oops, I'm going out of lines. Oh, you know what's it? I'm going to do that for you. There, let's leave it like that. And then, we are going to revolve this, sorry, about the line y equals 1. Y equals 1. So we're going to take this region and we're going to revolve it about the line y equals 1. Can you picture it? What's it going to look like? You ever played Parcheesi? Those little things you move around? No? Pieces? Oh, sorry. Yeah, it's the same kind of pieces, right? Yeah, kind of. I'm just... Okay. Well, the big question I'm going to ask now is every slice perpendicular to the axis of rotation going to be a disk or a washer? A disk. Because there's no space between the region and the line you're revolving it about. So, and then you don't have to draw the other side, but boy, life is fun when you do. Every slice perpendicular to that line is going to be a disk. There's no space. So you want to write down your formula for the disk method. volume equals pi. Don't forget the pi times the integral of r squared. Now, is this going to be a dx or a dy? It is dx, because look. Now, here's the thing to remember it. If it's either the x-axis or a line parallel to the x-axis, it's going to be dx. Okay? If it's the y-axis or a line parallel to the y-axis, the thickness will be dy. But this time, the thickness will be a small change in x. So important to get that part right. So now we're talking x coordinates for the limits of integration. We want to go from the smallest x to the greatest x coordinate of our original shaded region. So what do you think our limits of integration are going to be? 0 to what? 1. Yep, 0 to 1. Because you're adding these steps starting at x equals 0 and going up to x equals 1. You're adding them up to get the whole solid. I always like to put the square there so I don't forget to square the radius. Now, to get the radius, you have to know it's the distance from the axis of rotation to the outside of your shaded region. And just draw it in here. Right over here. So you always just work with the original region when you're finding the radius, okay? So it's the distance from the axis of rotation to the outside of your shaded region. How are we going to get that distance? How do we get a vertical distance? Y top minus y bottom. You're always going to be doing y top minus y bottom when it's dx. Okay, so what does y top equal? 1. Good. Minus y bottom. Y bottom's on the circle. What does y on the circle equal? I don't know. It's all mixed up in there. Yeah, if you solve for y, you would only take the positive square root because it's up on the top half of the circle where the y's are positive. Y is the positive square root of 1 minus x squared. And that's it. At this point, this one you would have to actually do in the calculator because if you did square it out, you'd have a radical term. I'll give you what the answer is if you want to try it out at home. I don't know if you guys are so fast, like you're probably like, got it. I don't know. This one turns out to be 0.301. Make sure that you do know how to enter it into the calculator. You know, some of you are such purists, and I love that. You always want to do them by hand, but you also have to be able to do them in the calculator because some you can't integrate. Like you don't have an x for each sub. Questions on that one? As far as the setup? Can try another one? So I want to draw, for number 2, let's figure out what region's enclosed, see what line we're going about, and to see if it's a disk or a washer. Y equals x squared. We know that one. Y equals 2x. That's just a line with a slope of 2. Get out of here, kids. Get out. So hopefully you've identified the enclosed region, and we have to revolve about the line x equals 2. I don't know where to put the x equals 2. I better find out where this point of intersection is so I know where to put the 2. I don't want to just like guess, you know. If we set them equal to each other, we set x squared equal to 2x. 0. Do you see what values of x squared intersects? 0 and 2. And I know already this is the point 0, 0. What's this point? 2, well, y is equal to either x squared or 2x. We'll get the same y. What is y when x is 2 on either one of these? 4. So I wanted to know where 2 was, because now I can draw the line in x equals 2. This is the line x equals 2. We will be revolving about that line today. Do you think we're going to be using disc or washer today with this one? Washer. There's all this space here. So if you do want to draw the other side, you kind of just like reflect over this side. Or do you draw your... Ooh, that was a bad one. Sorry. Outside, outside. But again, you don't have to do this. So you said washer. The formula for the washer method, we have the pi, then what? dr squared minus little r squared. Now, is this going to be a dx or a dy for the thickness? dy. See, if it's either the y-axis or a line parallel to it, when you figure out the thickness, it's going to always be dy, a small change in the y-coordinate. Oh, we could do the limits of integration. Once we know it's dy, we want to go from, well, you tell me, what do you think the limits of integration are going to be? 0 to 4, because you want to go from the smallest y-coordinate to the greatest y-coordinate. Now you're adding up this stack of washers to get the whole solid. So 0 to 4, excelente. Now I got to figure out how to get the 2 radii. And since it's a dy, am I going to be doing a y top minus y bottom or an x right minus x left? X right minus x left. So let's get the big R. Big R is the distance from the axis of rotation to the outside of your original shaded region. We said we're doing x right minus x left to get that. What's x right? 2, right? X equals 2 minus x left, that's x on the line. Oh, very good. You said y over 2. That was good. Usually people say 2x for that, because it's what x equals on the line. And on the line, x is equal to y over 2. All right, that's your big R. Radius the whole thing. Little r, sorry, big R, you got to move. Little r is the radius of the hole. It's the distance from the axis of rotation to the inside curve, right? X right minus x left. What's x right? 2. It's 2, right, guys? Okay. I thought you said that, then I thought I rushed you. Okay. It's not. Exactly. It's just that we get so used to minus 0, and now it's not. As long as you have that x right minus x left, it's all the same. And then x left is x in the parabola. What does x in the parabola equal? Radical y. On the parabola, that's the setup. So if you ever saw a problem that said set up but do not evaluate the definite integral to find the volume of the solid, this would be enough. That would be all the work you'd have to do. This one you could do if you wanted to square them out and do them all and spend the time, but you could put it in the calculator. You just pretend all the y's are x's when you put it in the calculator. And if you did that, for you kids that are curious, you get 8.378. If you want to note that down and make sure that you're able to enter those things properly. Yes? Yeah, when you put this in the calculator, I would put in pi, math 9. I would open up a new set of parentheses, 2 minus x over 2, close it squared, minus, open parentheses, 2 minus rad x, close that, close the parentheses squared, comma x, comma 0, comma 4. So the calculator doesn't know you have y's on the paper. You know, as far as the work you'd have to show me, that's it. But to put into the calculator, you just pretend all the y's are x's. I want to make sure you get that. So whenever you're doing these problems, you have 6 of these, you have a worksheet. First draw the region. Ask yourself, is it going to be disk or washer? Write the formula out. Get that dx or dy right. And once you've set up the integral, that's good. If you want to try to do a couple by hand, fine. If not, you can put them in the calculator. I really want to see that you can set them up, that you're getting these radii correct. All right?